uh, we finished actually the inductor in terms of concepts, and we established the following relation for the inductor. We said that for the inductor, V is equal to L di by dt. L is the inductance, and its unit is in Henry. And di by dt is the rate of change of the current. So this is the inductor. This is how it look like. So when we have a current I, we have a voltage V is equal to this, using or following the same passive convention we did for the resistor and the capacitor. And then we said if we want to find I, it will be 1 over L integration of V dt plus the initial condition of this is from 0 to t at 0. And also we found that the energy equal to 1/2 Li at T2 square minus 1/2 Li at T1 square. This is assuming that the inductor has been 2 period of times and it was charged at both of them. If the inductor was initially not charged, then the energy is 1/2 Li square. And we said that there is sort of duality between the inductor and the capacitor. Each time you see V changes to I, L changes to C, I changes to V, and then you will see the capacitor relation directly. Okay, so we have like a couple of questions. Let's see here. This question says here L is given to us is equal to 0.1. I of 0 is equal to 2. So there is an initial current which is equal to 2 amps. Then we need to find I of t for t greater than 0 and the energy stored between 0 to 2 seconds. How much energy we stored from 0 to 2 seconds. Okay, so basically the relation we have here, now we want to find the current from the voltage. So your I will basically be equal to 1 over L, the same relation I just covered with you. We will do the integration from T0 to T1 V dt plus I at T0. This is the relation that we will have. So your current I is equal to 1 over L, so it's 1 over 0.1. Integration from 0 to T. Okay, because I want to see the current relation from 0 to this T, which T is by the 2 seconds. Okay, but I will not substitute here 2 because if I substitute, I will have a value. It will give me the current at T equal to 2. But I want to from 0 to 2, so I want to see the relation in this range. Okay, so from 0 to T, so this is 2 dt plus my I of 0 here, which is 2. Okay, so this is 10 times 2t plus 2, or it's equal to 2 plus 20t. So this is your current is equal to this. Now, if I want to evaluate the current as a value, then I can draw this here. Now we start at t equal, this is your t, and this is your I of t. So we start at t equal to 0. We have 2 amps, so we start here 2 amps. This is where our starting point. And then we have a slope of 20. So we will go straight line, linear relation, until we reach 2. Now at 2, what will be the current at 2? Substitute 20 times 2, which is 40, plus 2 equal to 42. So here it will reach 42. Now, what will happen after that? After that, there is no voltage. The voltage is equal to 0. So what will happen to this current? What do you think, guys? What do you think will happen to the current? What is the value of the current? Okay, some say 0, some says 42. Actually, it is 42. Why it is 42? Now, I am charging the inductor with this current. I reach 42. And then I remove the voltage. What will happen to this charge? It's stuck in the inductor. It has nowhere to go. So the current will stay as such, like this, because there is no discharging process. I charged, remove the source, then you can look to it as follows. Your dad gave you $100, so he charged you with, and you took the money and you left and you don't use it. It's impossible. Of course, you will use it. Okay, but let's assume that. So you don't. So how much charge you have? You will keep this money will stays with you until you start buying stuff or discharging. So this is exactly what is happening here. It will stay as it is. Now, if you want to apply the relationship, we can apply it here. Okay, so I still equal to 1 over L, 1 over 0.1. Okay, now I will take the integration from, let's say, 2 to whatever the value, infinity. But the voltage here is 0. The voltage is 0, dt. Plus I at 2. The initial condition now is at 2. So all of this goes to 0. So what is left is I2, which is the 42 amps. So hopefully this is clarified things. Then it says here, find the energy stored. Now we just covered the formula for the energy. We said that the energy is equal to, the energy in the inductor is equal to 1/2 L I. Now here I at 2 square minus 1/2 L I at 0 square. Okay, excellent. So 1/2 times 0.1 times 42 square minus 1/2 times zero point 0.1 times 2 square. And if you find this, calculate this, so this is equal to 88 joule. So this is the energy that you store in the inductor from the 0 until you reach equal to 2. This is the amount of energy that you stored. So this is all the solution here in details. Okay, now let's see an interesting question, which is another typical exam problem. Here we have inductor and we have capacitor. We have both. Now we agreed about one thing, that the capacitor, because the relation between the current, the voltage is, and the capacitance I equal to C dV by dt. At DC, this is constant, so it means your I is equal to 0, and hence your inductor is an open circuit. Now, for the inductor, V is equal to L di by dt. So at DC, your voltage is equal to 0 because di by dt is equal to 0. And hence, you will have the inductor modeled as a short circuit. This is very, very important, and it's extremely fundamental to know how much energy stored in a capacitor or inductor when they are in a circuit. In the previous example, I just gave you inductor floating. It's not connected to a circuit. I just give you the relationship of the voltage, and I ask you what is the energy stored. Here is a different story. Here we assume that the the inductor and the capacitor, or we are actually not assuming we are in a circuit. I want to see what is the energy stored, although it's not stated here, but we assume the initial conditions equal to zero. Okay, so what we do basically, the inductor will be a short circuit, the capacitor will be an open circuit. So what is the energy stored in the inductor? The energy stored in the inductor, 1/2 Li squared. The energy stored in the capacitor, 1/2 CV squared. Now in this question, we know L and we know C. Okay, so the L here, 1/2, the L is equal to 0.25 I squared. And the C here is 2 farad. Okay, so this is 1/2 times 2 V squared. So what is left here is to know the current and the voltage, and now becomes a simple circuit analysis. Now what you want to use, any technique. Okay, so here we have a 4 amp source coming here. Now this is an open circuit, so we know that the current here is equal to 0. This is a short circuit. There will be a current, but there's no voltage, but I care about the current here. So maybe the best technique here is to apply current division. Okay, so this IL, the current that goes here, is the same current that goes here. But why? Because this is an open circuit, so it's the same current. So like we're having the 3 ohm and the 1 ohm, both they are in parallel. Okay, so your IL is equal to the main current source times the other resistance divided by 1 plus 3, which is equal to 4 times 3 over 4. This will cancel, so this will give us 3 amps. So this is the current that we have here. So basically, once I know the current here, I can know the energy. Very simple. 1/2 0.25 times 3 square, and from this we get this is 1.125 joule. Now this voltage is the same as this voltage because the open circuit is in parallel with this 1 ohm resistance. Okay, so what is the voltage here? The voltage here, VC, is nothing but this current, which is 3 times 1, which is equal to 3 volt. And from this you can, or from here you say this is will cancel, so this is equal to 3 square, or this would become equal to 9 joule. Now as I said in previously, now when I or when we are in the final, I will not specify any technique to use. So here I suggested to use voltage current division. You can use nodal as well. You can assume this is ground, this is a voltage V. Okay, so you can say that assume the currents are leaving, so we have V over 3 plus V over 1. This is enter the node, this is equal to 4. Multiply everything times 3. So this becomes V plus 3V equal to 12. So from this, 4V is equal to 12, or V is equal to 3 volt. Now the V is the voltage between this point and the ground. IL is this current. So your IL is equal to this voltage, 3 divided by 1, we'll get 3 amps, the current that we just get from the current division. So this is why this is you did that in 2 steps. So there you did it only in one step. So there is always more efficient techniques to solve the circuit. But as I said, I will not be picky in the final. It's up to you to use any technique that you are comfortable with. Now, the last thing that we want to do is in the inductor is inductors in series and inductors in parallel, same like the capacitors. Now, when the inductors, they are in series, basically you add them. So the inductors behave like the resistors. When they are in series, you add them. When they are in parallel, 1 over L equivalent equal to 1 over L1 plus 1 over L2, etc. The opposite is in the capacitor. Okay, so this is how you do the parallel series resistor. So let's see this nice example. Okay, so in this example, we have couple of inductors in parallel and couple of inductors in series, and we want to find the total. As we said, I'm interested at this side, but we always go to the other side because at this side it's very hard to identify anything in parallel or in series. So we can see here these two are in series. You add them, so this becomes 60 millihenry. Now these two are in parallel, so they are in parallel. You multiply them and you divide by their summation, so it is 30 times 60 divided by 30 plus 60, everything in millihenry, so this is equal to 20 millihenry. So here we will have as 20 millihenry. Now this 20 is in series with the 100. So now all of this become only one inductor in series with the 100 millihenry. So this becomes 120 millihenry. Now this 120 millihenry, which is the equivalence for all of this, is in series with, sorry, in parallel with the 40. So now here we will have the 40 parallel with the 120. So it is 40 times 120 divided by 40 plus 120, and this is equal to 30 millihenry. So until this point we have 30 plus 20, so this becomes 50 millihenry. Now 50 in parallel with 50, this is the last one, so we have 50 times 50 divided by 50 plus 50, which is equal to 25 millihenry, and this is the equivalent inductance. And we said before, when you have two inductance in parallel, the equivalent that they are equal to each other, the equivalent one will be half. Now this is a very interesting summary of all what we have done, and I really encourage you guys to try to understand this, try to see how this works. Okay, now we have these are all the passive elements that we have so far. We have a resistance, we have an inductance, and we have a capacitance. Okay, the resistance, it is in ohm, inductance in Henry, capacitance is in farad. Now there is a relation that governs the voltage with the current. If I want to find the voltage in the resistance, it's R times I. If I want to find the voltage in the inductor, is equal to L di by dt. If you want to find the voltage in the capacitor, it is the 1 over C integration of I plus K2. K2 is nothing but the initial condition, the V at T0. Same thing if I want to find I equal to V over R. I is equal to 1 over L V dt, and this is the initial condition of the current. I equal to C dV by dt. The power here is I square R. The power in all of them is VI. Okay, but the formula will be different. Any questions so far? Everything is clear? Let me see if this thing here. Okay. Okay, very good. So we will have a few minutes of sensors, and then I have some interesting bonus questions for you guys. Okay, so we'll just finish the sensor part, and then we will have some good bonus questions that we would like to examine together. Okay, so we will talk about capacitive sensors only, not inductive sensors. Inductive sensors are hard to explain. It need more visualization. If it's in the class, I can show it to you more. But capacitive sensors are easy to understand. Now, if we take a parallel plate capacitor, we know that C in a parallel plate okay, with distance between the plates D, cross-sectional area A, and this dielectric material in between with epsilon 0, epsilon r. In some books, by the way, epsilon r is called K. So sometimes you see it epsilon 0 times K. So the capacitance C is equal to epsilon 0, epsilon r times A divided by D. So as I mentioned before, the capacitance change if you change two things. Either you change the geometry, the D and the A. Now, this is only for parallel plate. If you have other forms of capacitors, like coaxial, you will have a different parameters to play with, but it's the same principle that you're changing the geometry. Or you change the material inside. If you change the material inside, then also you change the capacitance because you are changing the epsilon r. Now, capacitive sensors are based on this principle. You either change the dimensions of the capacitor or you change the material inside. So the way you design your sensor, you make it with these things changing with respect to the physical property that you are measuring. And then by measuring the change in the capacitance, you can figure out what happened or what is the original change of the physical property. Remember, always remember that the sensor is a device that changes a physical property into an electrical one. Here is a change in the capacitance, which we usually make it also further change into a voltage by having also a Wheatstone bridge, but we will not go that deep in the sensor. So let's start with the displacement sensor. And we discussed a displacement sensor based on resistive principle before. And we said that by changing the resistance and they act as a voltage divider, then you can figure out how much you change in the displacement. Now, these displacement sensors are used, for example, to measure the what is the tilting or the damage that happened in this slab of cement. You are applying a load on it and start to yield or start to deform. So you are measuring this deformation using this displacement sensor. Okay, so here it is what I just mentioned. So basically you have connect to this in a certain way the sensor that one part is fixed, the other part is moving, and the other part is moving with respect to the movement part of your system. The change in the displacement that you want to measure, you connect it to this movement part. Now, as I said, the capacitance is epsilon A over D. Now, A is the effective area between the two plates on top of each other. So we don't consider this or this as part of the area. They have to be on top of each other. So if I move it in this way or in that way, I am changing A. I'm reducing A as a matter of fact. Then this is how it's done. So when you have the movement in this part or the displacement in this part, so then you will have a reduction in the capacitance. The more displacement you have, you are more pulling this plate, you are reducing further the overlapping area. So it's always decrease, 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 and then the capacitance is decreasing. So you are measuring the change in the movement or the displacement by change in the capacitance. Another way is to use the same thing for the coaxial as well. Same thing for the coaxial capacitor. Here this is the fixed part, is the outside part, and the inner part is the part that goes in and out with the displacement. So here your L will be changing because as this goes up, L will be reduced, and the same thing, the capacitance will be reduced as well. There is no change in B or A, they are fixed. There is no change in the epsilon. Here it says epsilon 0 without epsilon r, because the material inside is air, and epsilon r for air is equal to 1. So this is one type of sensor. Another type of sensor is level sensor. Now you have a container of water or any liquid, and you want to know the change in the level. There are two different types of monitoring systems for the water or for the liquid level in general. One of them is called continuous level monitoring. This will give you the height. Okay, if this is the total height is 10 feet, give you 8 feet, 6 feet, so it give you a continuous number, 4.6 feet, etc. Okay, and there is another level of sensors which is give you like indications. Are you, is the level is high or low? Now for those ones we use different technology. We use ultrasound sensors, something similar to the cars in the back bumper or the front bumper. When you come close to an object, they start to beep. Okay, how this beeping happening? There is some acoustic signal goes to the object and return, and based on the going in the two directions, so uh, you know the speed and you know the time it took, so you can figure out the distance of the arm closing to the subject, then you will start to beep. So this is one way, and there are some other technologies, but the capacitive sensor can be used to continuously measure, so it will give you the exact number each time. This is the explanation of the capacitance. Here, I will not go through this because we already explained this. But let's understand the principle here. As I said, you change the capacitance by changing either the material inside or the dimension. In this type of sensor, we don't change the dimension, but we change the material. Basically, the material is composed of two. We have air, and in air, epsilon r is equal to 1. And then we have water, and in water epsilon r is equal to 80. So there's a huge difference between the epsilon r of water and air, so the capacitor value will be significantly changing. Now here it is the height h, this is the formula. This k is nothing but epsilon r, okay, which is for the water in this case. Okay, so the total capacitance is C free plus C filled, and they come up with this formula. Okay, now once H start to increase, so this part becomes higher and bigger. So as H start to increase here, you will start to see that there is an increase in the capacitance. The capacitance will start to increase, because this is 1 minus, this is a negative number, 1 minus 80, so this is minus 80, so this is a negative number. So now with once this start to increase, then this becomes, the total becomes like a positive number, minus becomes a positive number. So this, as H start to increase, your capacitance start to increase, and this is, you can see it here. And there is a calibration curve. If you remember what we said about calibration, in every sensor there is a calibration between the change in the electrical property, this is one thing, and the change of the physical property that I am measuring. The physical property I'm measuring here is the change of H. So this change in H, which I want, is calibrated with the change in C. Here is the C. The C is in the Y-axis. Here it is the X-axis, the H. So I'm measuring this, but it reflects this. So for example, if we have a C is equal to 3, so this is around 15 point or 17 point something. And this calibration is done in the electrical system to give you, it will not, you will not see this value, you will see only this value, because this is your interest in your screen or your LED or whatever system you have to show the results. But this is done internally. This calibration is done internally. Finally, soil moisture sensor. We talked about this also, this technology used in resistive sensors, and we said that if the water is, I mean, if the soil is has wet, then there is moisture. The moisture has certain conductivity. You are measuring this conductivity. Now, this is using the same principle I just mentioned. Again, you will have a capacitive sensor here, and when you have a soil that is dry or soil that is wet, the difference here will be like soil. Soil is dielectric material, so the epsilon r for the soil is between 2 to 5, and then air in between, there will be air, so epsilon r of air is equal to 1. Now when this is wet, so it is soil again with the same dielectric constant of the soil, epsilon r is equal to 2 to 5, but here you will have water, so epsilon r of water is equal to 80. It's very, very high. So the overall dielectric constant here will increase because of the wetting factor. So by measuring the capacitance, if you have a very dry soil, it will give you a very low capacitance C. If you have a very wet, you will have a higher value. And if you do some sort of calibration, then it can give you some value. And this is how it's called here capacitive soil moisture sensor. This is how it looks like. Of course, there is some electronics here to do the conversion. If there's any calibration, how to present the results. So there is always certain electronics. And here you see the sensor we just inserted in the soil. And we mentioned before that why we need to do this. We need to do this because I want to automate the irrigation process. I don't want to just give water every time. Whenever the soil is dry, whenever these sensors start to sense that my soil is dry, it will give a signal to a water pump to run and start the irrigation process. And this is done, I mean, as we speak in the modern farms, this is how it's done. It's not done manually. You sense the moisture, and then based on this, you will feed your water. Okay, now here, stop here. Let me just add a couple of pages here for the bonus questions. Hopefully, guys, you are ready for the bonus questions. Okay, we have a lot of questions. Let me see how much time I have. Okay, not much. So let me just start with something funny, interesting. Let's start with this question. Okay, so let's start here. It's about the energy. Okay, so we have this circuit plus minus 12 volt. I will have here a capacitor C. I will have here a resistance, and its value is 200 ohm. Another 100 ohm resistance. So there are two resistors, 200, 100, and we have an inductor here, 0.1 Henry. Okay. So the question says here, what is C? So you need to find the value of C so that the energy stored in the capacitor is equal to the energy stored in the inductor. Go ahead. What is the value of C? Now, remember, I will give you a hint here because this is new, relatively new. Remember, the capacitor C will become equal to an open circuit. The inductor will become equal to short circuit. So the inductor will be open circuit. Sorry, the capacitor open circuit. The inductor will be a short circuit. So this is what we know about this. What we know is that the inductor is an open circuit and sorry, the capacitor is an open circuit, the inductor is a short circuit. So you need to equate these two conditions. There is no need for nodal. This question, you don't need to go for nodal. I would suggest just simple KVL. Nodal is too much. It will end up one loop. So it doesn't need to have to go for nodal. So omega WC, so you know that this is 1/2 CV square will equal to 1/2 LI square. So this is the criteria that you will use. C equal to 5. No, not 5. Try again. No, omega L is not equal to 0, cannot equal to 0. Omega L equal to 1/2 LI square. Remember, when we have a short circuit, the voltage is equal to 0, but the current is not equal to 0. When you have a short circuit, there is a current, but there is no voltage. But the inductor energy is 1/2 LI square, not 1/2 LV square. So there is an energy in the inductor. It's not equal to 0 and cannot be equal to 0. Is that clear, Alexa? It's good you guys give me your thoughts. So I really, this will help me to see how much you are understanding so far from some of the concepts. Okay, guys, continue. Still, you have the chance to win. Okay, Grace. You are very close, Grace. Very, very close. Sanya, no, you are a bit off. Okay, 2.5, exactly. We have a winner. Sorry, Kim. Grace was just faster than you. Okay, so let's answer the question. Let's answer the question. And this is what will end up my lecture today. Okay, so let me answer the question here. This is a typical exam. Actually, I got this from exam. I took this from one of the previous exams I gave to the students. So this is a typical exam question. So I will keep this here. So I will redraw the circuit. It's very important to redraw the circuit so that you will not do any mistakes. So this becomes equal to this. Here I will have 200 ohm, and this will be open circuit. This is your VC. Continue. We'll have 100 ohm, and then we will have a short circuit here. So this is the current I of the inductor. This is your VC. Now, this IL is the current that goes here, is the current that goes here, is the current that goes there, because this is an open circuit, so it's just one loop. And this is 12 volt. So your IL is equal to the 12 volt divided by 200 plus 100, just 1 kVL, 1 kVL, 200I plus 100I minus 12 equal to 0. So from this is equal to 40 milliamps. So now what is VC? Your VC is the current times the 200 ohm. So it's equal to 40 milliamp times 200, which is equal to 8 volt. Now we are set to put the quality relation. So 1 half times C, which I don't know, V square, which is 8 square, is equal to 1 half L, which I know, 0.1, times I square, which is 40 times 10 to minus 3. And very important to keep the unit here, square. The half will cancel with this. So your C is equal to this. Divide by 8 square, and you will get 2.5 microfarad, or equal to 2.5 times 10 to minus 6 farad. So this is the answer. Well done. Grace, please send me your ID to add the bonus mark for you. So that's for our today's lecture. So we will have a new topic starting from Thursday, and this topic will stay with us almost to the end of the term, which is, as I said, this is the AC analysis. In the AC analysis, we will not learn much of electrical engineering concepts, but more of the math tool that we need to deal with the circuit. But we will have back examples: KCL, KVL, voltage division, current division, nodal analysis. We will redo everything. However, the only variable will be changing is the math. So this is why it's very, very important, the Thursday class and early next week, because this will give you the base. Okay. And in short, this is the math you learn to deal with vectors. What we'll be doing here, the difference between DC and AC, is exactly the difference between dealing with scalars and dealing with vectors. When we add scalars, we just add magnitude. When we add vectors, you have a magnitude and you have a direction. And you have to make sure that you add them properly. You cannot just add the magnitude of the scalars if they have different angles. So that's basically what we will be tackling on Thursday. Nice meeting you guys. See you on Thursday. Bye now.